Today's representative lecture is a part of his research program in our institute. Ladies and gentlemen, let us welcome Professor Yoshihiro Shibata, who will deliver the 19th Eduard Cech lecture entitled R-Solver Approach to the Maximal Regularity of the Free Boundary Problem for Navier-Stokes Equations. Professor Shibata, the floor is yours.
Thank you so much. It's a very great introduction of the Professor Eduard Cech. I'm very proud and also very honored, very happy to invited to be here and then give my talk about my recent result in this very honored Eduard Cech visiting positions. And then also, now I remember that when I was a student, I learned some the general topology, the Czech cohomology, and so on. I really surprised. Yes, I'm very much honored to be here now. So first of all, I would like to talk about I would like to talk about the R-solver approach to the maximal regularity of the free boundary value problem for Navier-Stokes equations. But anyway, first, I would like to thank not only the Professor Eduard Cech, but also the Professor Sharka Nechasov for the kind invitation to here. And since 1990 something, first time 1992 or 3, I invited for some summer school. This summer school is still going on. I mean, every year, very influenced very much to our mathematical fluid mechanics groups. I really thank to your contribution to this one. And then I met many excellent mathematicians here. I remember that, of course, Professor Nechas is the father of Sharka, and then Sharka, and Edward, and Anna, and also Milan Pokorny. Sorry, I remember very much, but Kretschmann is correct. And okay, Thomas and Andre Kremer. Excuse me, the pronunciation of Czech language is quite difficult for me. I'm sorry. Excuse me. Stress club, it's okay. No.
Another Andre Kremer.
Oh, yes. I want to say. Sorry. Excuse me. It's very difficult for me. And also, finally, I want to mention that Anthony Novotny is also my very good friend, but unfortunately, he passed away recently. He was a little bit younger than not a little bit, very younger than I. Okay, so now I start the picture, of course. Yeah. Honey, okay, so some kind of typical fluid. The honey is too much viscosity. And then the beer is your specialties, and also the specialty of my countries. Yeah, because actually, the long time ago, some guy who started Japanese beer came to Europe and then travel around, drink to beers, and then finally Czech beer is the #1. So our beer, if you count my country, then you feel some of the Czech beers. This is true, I guess. Okay. And then tornado is a very big motion of fluid. And the airplanes. So this kind of thing is now maybe later why airplanes lift. I a little bit explain. Okay, then I should start the equation. So the rho and mass density and velocity is typical two quantities to describe the fluid motion. And then first equation is the conservation of mass. first is the conservation of mass, and the second is the conservation of momentum. And then maybe you know well, but it's better to explain now, maybe. So it's you consider some fluid particle, and then omega is a fluid particle, and then gamma is the surface, and then a normal component. So n is normal to the gamma, and the flow fluid and the velocity u, and then rho is the mass density. The change of mass density is just integration on here. How to consider the change? It's just n dot u is the normal component of the velocity field. Is now is times rho is a total mass entering inside of the omega through this gamma. So it's written minus is going to inside, yeah. And then gamma, so rho n, maybe u dot n, this sigma is the integration on this surface. But then using the Gauss theory, is changed to the volume integral dx. So you have, okay, so this integration is into here. Then you have rho t plus d rho u is equal to 0. This is the derivation of the mass conservation of mass. And the second is really Newton's law. It's mean, but then what is this? It's acceleration. But it is we call it the material derivatives. But how to get this one is usually we watch the fluid motion in so-called Euler coordinates. So that we have, for example, here is the Euler coordinate, and then flow is passing us. Sorry, it's okay. No, the flow is passing. Then you consider some ordinary differential equation. So x is the coordinate of the flow, and dx dt is you feel the velocity usually. You watch the flow, but you feel velocity, right? Therefore, dx dt is important. And then this is just ordinary differential equation is equal to u xt. This is hold on here. And then you solve this ordinary differential equation, then you get flow. Maybe start from some y point y. Okay, then you calculate acceleration on this is x t. Okay, forget y. Okay, t. And the acceleration, therefore you applied time derivative. Then you get the differentiation of composite functions. So ut here, and then the differential here is x dot t, and then nav x u. It's okay. So it's just the composite. Okay, differentiation for the composite functions, and then x dot t is really this one. So you have this. So this is acceleration of the velocity on this flow. So and then the times rho is equal to f power force. This is a Newton law. So then the question is what is f? Maybe come later, but anyway, just give the div t over u p is our forces for the flow. And then okay, so now we come to the Euler, of course, first. because Euler is the first mathematician who rigorously consider the flow, fluid flow. And then this, I don't know where, but I heard when long time ago, someone told me that Euler want to formulate. All right. Euler want to formulate the problem by using the Newton law, but the Newton law, unfortunately, written in the Newton law, I mean Principia, is written in a geometrical way. There is no PDE. Then, thank you. Then, no, I don't do red. This one, okay. Sorry. I push wrong buttons. Excuse me. So it's Euler. But then Euler want to formulate the fluid motion, but the Newton Principia written in a geometrical way. Therefore, he create the ordinary, so the PDE, meaning is to describe this equation. And then he found this one, and is equal to nabla P. So P is the pressure on, so each fluid particle is just give some pressure. And the pressure is a scalar because there's no direction of each other. Therefore, sorry, this is next. Oh no, sorry, excuse me. Okay. So Euler found this equation, so-called nowadays said Euler equation, with divergence free, because now therefore simplicity, so rho is constant. Excuse me. Now rho is constant. We assume constant. Then from the first equation, you have d is equal to 0. Yeah. So this is incompressibility. But anyway, so under this condition, so he considered this Stokes Euler equation, and then he derived, and after Euler, there are 200 years. There are a lot of the theory was derived from these equations. But then a typical point is that if you have vortex, then vortex never disappear. So once in a flow, some vortex rings disappear, then this is always never disappear. This is the Euler, the characterization of Euler flow. If you look at the flow, and then you find vortex, but this it's continued forever, then you can say this is Euler flow. Right? But then the next page is, oh sorry. Now the Navier appear. This is Navier. Then Navier, as far as I know, that he was the engineer of making the bridges in France, and then the watches maybe Seine rivers. Then what's the Seine rivers? Then he found vortex, but maybe I'm not so good at writing Seine river. He watched it maybe on the, I don't know. But then there's no vortex, but near the bridge, the vortex appears. And then this flow is going out, then this vortex disappear again. So he found this one. And then he finally found the viscosity. So it's the fluid should have the viscosity. It's a final conclusion. And then he put Laplace operator here, minus mu. This is viscosity for him. But unfortunately, his derivation, as far as I heard it, his derivation is not so mathematics. Then finally, famous Stokes derive correctly this mu Laplace U. So this is represents viscosity. Okay, so it is so-called Navier-Stokes equations but it is describing the incompressible cases. But anyway, so then how to solve it? But before the mathematical study, then after Stokes, as far as I know, that it's the Ozen is studied the so-called stationary problem for the Navier-Stokes equation nowadays. It's okay. So his book is more than 300 pages. I don't know. Ozen is maybe Swedish, but anyway, written in Germany. And then he especially analyze, that's called Ozen kernel. But for example, there is okay. So airplane. The fluid here. As you know well, that then you have a lift and resistance. So he analyzed this kind of things, and then so the airplane moving this way, then you get a very strong lift. They get this analyzation is maybe come from the Ozen. You can therefore my engineering colleague, my friend, said to me that this is engineering Bibles still now. And then the mathematical study of so-called stationary solution is maybe, as far as I know, that the Professor Finn continue of the Ozen. He wrote of works, and then now continued the Professor Nechasova and the Kretschmer and the Neil Stupa. So, and then this he preparing some nice books. He is maybe this is just continuation of this. I think Ozen books. Yeah. Okay. So this is the beginning of the stationary solutions. But then now famous Relay. The Relay proves the existence of weak solution of Navier-Stokes equation. It's if you remember. Okay, so now our equation is mu. Sorry. Plus u plus t. Okay, 0 and the divergence u 0. And then you multiply u, and then you take this equation, and then the integration by parts, and then thanks to this one, you can drop this term and this term, and then okay, so forget the details, and then you get this equal. It is actually the solution is regular than it's equal, but you have this kind of energy inequality, we say. Energy inequality. And then Relay, and then Relay also the Schauder, the proof existence of a weak solution of this one. And the idea is just a fixed point. It's a very elementary idea is the Brouwer fixed point theory. Fixed point. Also, the first course of the analysis on calculus, you consider continuous function on this, yeah, and then y and x, and then you write line x equal y line. Then always there's some fixed point. This is Brouwer, the elementary version of Brouwer fixed point theory. And then, so if, okay, so this is generalized, in some sense generalized by Schauder to the infinite dimensional cases. And then, of course, this inequality, oh, sorry, no, this one. This inequality gives you some kind of compactness of some infinite dimensional spaces. Therefore, you can find the fixed point. And then you can show that existence of a solution, but weak sense. This is Ray and also Ray-Schauder ideas. And it's now also. And then, but another approach is the HOP. I think maybe this one got it. Maybe I'm wrong, but I don't know who is the first. But anyway, HOP, he used the Galerkin method. It's like it's UN is some kind of finite number of expansion formula you have. It's xj is the basis of some spaces, and then you consider the finite cities, and then plug this formula into the equations, and then you get some like a relationship of AJ, and then the problem is at convergence, and going to infinity. Then of course you can easily show that the convergence, but the point is that this function satisfy the limit function satisfy the nonlinear equation or not. This is a problem, of course. And then, but anyway, it can be proved, this one. And then, so this way is a HOP way, maybe. So nowadays, say, Roulet-Hopf solutions for the solution to the Navier-Stokes equations. Then, as you know, you understand well that if this is only one fixed point, but it is also possible to the several fixed point, even for this elementary problem. So big problem is the uniqueness of weak solutions. And then two-dimensional case is Professor Radenskaya proved uniqueness of the weak solutions. So big problem is a three-dimensional case. It's now a millennium problems, they say. Okay. Anyway, this is the problem for the weak solutions. And then now, oh, sorry. Now, yes, Eduard, have you also answered? Now, this question is, of course, to go to the compressed viscosity case, compressed viscous fluid case. So again, we have equation, conservation of mass. Now that you consider full equation, and then a Navier-Stokes equation here. But then P is a pressure field, and pressure P and rho, if there is, this is three unknown, rho, U, P, and the equation is a 2. Therefore, in order to solve this equation, you need some kind of relation. So usually we use the P is alpha, rho, gamma, the barotropic cases. Then under this condition, okay, so this is really two equations and then the two unknown. And then first, okay, so there are a lot of argument, and then Pierre Lyons proved weak existence of weak solution with these equations. But then, okay, some argument is still something okay, so mysterious or something like I don't know, I cannot say it. Then finally, Eduard gave some perfect proof for the existence of weak solution, and then, but still gamma is positive, no. So the ideal gas case is the open. Okay, gamma equal 1 is ideal gas, is a classical one, it's still open. Gamma is needs some negative positivities. But anyway, Eduard and the Czech group work a lot and then contribute a lot of the weak solution to the compressible Navier-Stokes equation. Then my friend Anthony also contributed a lot. Okay, so this is the weak solution case, the compressive case. So far, okay, so we know existence of weak solution for any initial data, no restriction of the size of the initial data. But then the problem is the uniqueness. Okay, so then the topics is a change. Why? Because the uniqueness. This then now unique existence of strong solution is a different topics. It's the one of the goal for it is work on this is my topic. One of the goal is a local in time unique existence of strong solutions without any side assumptions of initial data or small initial data, the global in time unique existence of strong solutions. This is the goal of studying the unique strong existence of unique strong solutions. So it's and then these studies, they compared with the weak solution. These studies a little bit later, maybe after Second World War, because we need more PDE techniques in some sense. As far you remember that the weak solution case is very topologist, and it's more important. But then to show so far to show that we need more hard analysis. So it's quite a different thing. No, maybe they're not so quite different, but anyway, a bit different. Okay. Then I want to give you some rough ideas how to solve the classical existence of strong solutions. So then I have to talk about the analytic semigroup. So let X and Y the two Banach spaces, and you consider operator A from X into Y is bounded to linear operators from X to Y. If you consider this operator Y to Y, then it's just closed operators, closed to linear operators. And then you consider this ordinary differential equation in abstract sense. So T positive, you have this equation, and then initial data here. Then the Hira-Yoshida method, so-called Hira-Yoshida method, is considered the corresponding resolvent problem. So DTU changed to the lambda, the multiplication of complex number lambda, and then you consider this equation. Okay, so assume that this equation has a unique solution for Ux here, because the operator A is going to X to Y, therefore V should be in Y. Sorry, excuse me, it is V, not U. Excuse me. And then the important assumption is that this V satisfies so-called resolvent estimate. So lambda times V is bounded by F for any lambda. Now I talk about only for the parabolic type. Therefore, lambda here, sigma sub epsilon is so-called parabolic sector. Sigma epsilon. Complex numbers of argument lambda pi minus epsilon, and then epsilon is just pi over 2. So in the complex plane, okay, pi 0. So this is epsilon. And then why you take this one is, of course, the solution is the given by Fourier inverse transform of D. But then Fourier inverse is now by using some kind of theory of one complex variable. This Fourier transform is moved to this sector to analyze the solution U. So important assumption is that V is defined on these sectors, in sectors, and then having this estimate. Then you can show that this Fourier inverse transform is well defined and okay, have nice properties. Especially you can show that the T is positive, then okay, UT is just Laplace Fourier inverse transform V, and then the U is satisfied this and the initial data this, and then we say usually the continuous analytic semi-group T of T is they generated under this condition. And then this T, operator T, gives you the solution. The solution U is given by initial data, T of T initial data, plus convolution operator T, T minus S, Fs, right hand side. This is the solution formulas. Okay, it's some kind of fundamental formulas for the ordinary, this abstract ordinary differential equations. So the point is that on this sector, you have this estimate. Okay, once you get this estimate, then automatically you get the generation of semi-group, and then you have the solution formula for this equation. Then this is a linear equation. Then the Professor Kato and Fujita and Kato, my country, but also maybe Russia. I don't know where, but once Professor Fujita said that in some meeting in Russia, maybe his theory is famous. Fujita Kato approach is very famous to the Navier-Stokes equations. Now I tell you. But also at the same time, maybe Russian, the Sobolevsky or something, they proved the similar things. But unfortunately, 90-50 days, there's no connection with my countries and the Russians, and then even they wrote papers with Russian languages, and then only very short papers. So it's quite difficult to communicate each other. Therefore, in some sense, independently prove that the similar result. Anyway, I am Japanese, therefore I want to explain the Professor Fujita Kato method. Right. Now, again, we consider the Navier-Stokes equations, but with zero boundary condition, non-slip condition, we say. It's a most typical problem for the Navier-Stokes equation and the fluid motion. Fluid motion. Okay, so fluid is here, and then outside gamma, and then you have the fluid motion. But then on here is the velocity field is zero. It's a very typical situation of you meet many times. Of course, there are a lot of problems, but anyway, local in time solution is okay. So you can show some nice local in time existence theorem nicely. Anyway, you consider this equation. Then forget about this nonlinear term first. The Kato Fujita consider this Stokes equation, we say. And then they prove the generation of analytic semi-group to this Stokes equations. Okay. So then if you remember the formulas, the last pages. So let's say that T of T is the Stokes semi-group associated with this Stokes equation. And then you move this nonlinear terms to the right-hand side. And of course, the pressure term P is, you eliminate so-called solenoidal projection. Then you have this formula. So solution U is by using the Stokes semi-group. U is given in T of T initial data minus integration from Z to T minus this convolution. And the P is a solenoidal projection. So if you project P, then this number P is disappears. Okay, so forget details, but anyway. And then you have this formula. And then you can solve this integral equation. It's like the usual ordinary differential equations, the same ideas. Just give U, or say B, and then you give U D here, and then you define U by using this, and then you iterate the many times. Then you find the fixed point. Then you can say at least there exists some small time t. Then you can find the fixed point of this integral equations. And then, so this is roughly speaking, this is the ideas of Kato Fujita. And then you can show that the local in time existence of this Navier-Stokes equations. And then also the global in time for small data is the same ideas. Okay, now skip it. Okay, rest of my time is maybe I want to talk about the free boundary problem, but it's a more technical thing. So if you have any question now, I want to get. It's okay. May I proceed? Because now maybe talk my own things. It's okay. Yeah, okay, please.
Just when you, and this is really interesting, it's just historic. So when Lere wrote this paper in 33, 34, he did this so-called Lere conjecture, and this was open for a long period. And then when was, let's say, solved that there is only a trivial solution. So this is this paper of Nečas, Šverák, Ružička. So he wrote, let's say it is somehow it is sad, but it's true. He sent last paper, let's say last letter to my father, and he explained why he did not follow, why he did not investigate, study this problem, let's say for Navier-Stokes. And the reason was that he discussed with Sobolev, and he told him, no, this problem is very stupid, so don't study such problem. So this was reason why Lere gave up this problem. And maybe another thing is just, which was not mentioned, that nowadays there is already this 3D case for uniqueness. For Navier-Stokes case, it's solved. There is this result of non-uniqueness. Yeah. But what is millennium problem, which is more or less still open, is regularity. So still you can do. Just to tell this.
Okay, thank you very much. Very nice comments. Maybe I will proceed. Okay, thank you. Okay, then I want to talk about my topics. It's a free boundary problem. Yes, of course, now the equation is very much complicated, but the situation is if we draw the picture, then the situation is very easy. Now you consider, for example, the motion of ocean. We are faced with the Pacific Ocean. There is, I don't know, Czech has no big ocean, so I mean, no. So maybe you're not so interested in the ocean problem. But why ocean is we need some depth anyway. Okay, then okay, then let's say that it's a domain omega sub t, is the domains depends on time because of the surface is moving. Then this is water, therefore is Navier-Stokes equations. So here is Navier-Stokes equation. It's a first line. First line. And then the boundary condition here, boundary, we have boundary. It's an unknown domain, but anyway, you can consider the normal direction. Then T is the so-called the Cauchy stress tensor. I already gave you some assumptions. Then, so the Cauchy stress tensor is here, but it is normal component of Cauchy stress tensor on the boundary. Tn. Usually, some surface tension comes in. Is because you have usually if you look at water, then you have surface tension because. But now, okay, so for simplicity, it's 0. Yeah, of course, you put the surface tension, gravity, forces, and so on. It's a quite difficult problem to solve. Okay, so for simplicity, it's 0. Right? Then you have, and then third. Oh, sorry. No. And then this one. This is the condition that so the evolution speed along to this direction is b gamma t, d omega t. Evolution of this surface, or evolution speed of this surface, so this direction, we say v, but this is just the same as d dot nt. I mean, the same as the velocity field, the normal direction should. Otherwise, you have some gaps or flow is outside. So it's a so-called non-slip condition, but it is a very kinetic condition, but it is important to consider the problem. Anyway, so this is a full system to describe the free boundary problem. And then, okay, then omega sub t is the unknown. So unknown is not only V and the pressure P, but also this omega sub t is unknown. So one of the typical way, it's maybe I learned from this Professor Solonikov papers, it's use so-called Lagrangian transformation. Meaning is that, okay, so again, you ask the flow where you come from. So we watch the flow here. We watch here is Euler coordinate. But then you ask, is time t. This flow starts from here, and then time t is coming here, x. So it's a so-called flow map again. I already gave you that the ordinary differential equation that you solve. Okay, assume that solve, and then you get this one. And then this flow start here. This flow, this omega is a fixed. So you consider the inverse map of this one, right? So y equal phi t minus x. Of course, we assume that we have inverse map, but anyway, okay. So it is under the solving the problem. Therefore, okay. Anyway, we assume that the existence of the inverse of this flow map, and then the change of variables, so on, and after some calculation, you arrive at hey, where is okay. Okay, finally, very complicated equations, but it is Stokes equation is equal to some terrible nonlinear terms. Nonlinear terms gives this kind, and the divergence condition also becomes non-homogeneous nonlinear term here, and then the boundary condition it becomes also nonlinear terms. on the initial data. So a good point is omega is now fixed, but the bad point is a very, very terrible non-limit term is the right-hand side. That we cannot find any conservation or something. Just we try to solve by the hard analysis, right? Okay. Then final point. Now I come to final point. Excuse me. Okay, now again, I want to explain you how to solve it. So the how to solve is really, excuse me, no. Doesn't move. I don't know. Okay, but it's a necessary slide. Okay, but anyway, first again, I want to use the fixed point. Sorry. So now the abstract way, our equation becomes to fu and du is equal to gu, right? Then you give b and then you solve this equation fb and bu is equal to gb, and then you consider the correspondence of b to u, and then you find the fixed point for this correspondence. So again, the important point is that how to analyze of these linear equations. Okay, let's then the final 5 minutes. I want to talk to you some how to solve this equation, but this I want to get back. Okay, now it does work. Thank you. Okay, good. Okay, so now I want to consider this one, but the different point from the Professor Fujita and Kato is now I should consider G, non-homogeneous initial boundary data. It's not the standard the semi-group theory. But anyway, you apply Laplace transform. It's like a Fourier transform. Apply here, and then the point is that this time derivatives again multiplication of the complex numbers, and then you apply the Laplace transform. Okay, let's say that u hat is a Laplace transform of u. Now is you have this equation. Then you solve this equation. It's much easier than compared with the time-dependent problem because the unknown, I mean, it's one variable is missing. It's much, okay, not so, can say easy, but anyway, becomes much easier. All right. Then, next. Oh, wrong direction. Okay, then, anyway, you find the solution operator S of lambda. Is but then the point is one point is that now not only f if you said solution operator, then okay, right. Now our okay, it's okay. Thank you. Now our problem is now we have a boundary data here. G. Then solution U in some sense how depends on this boundary data F is F, but point is that now some kind of the fractional derivative of G hat and G hat. This triple is going to solution U. So this map, I write S lambda. So S lambda gives you the solution operator, but the important point for the boundary value problem case is not only F and G, but also lambda alpha G. So this is corresponding to some kind of fractional derivative. So you have to consider fractional derivatives on the boundary. It's maybe some kind of different point of the the zero boundary condition case. And then you have this solution operator anyway. Then the Laplace inverse of this gives you the solution to the time-dependent problem, right? Then, honestly, I have this story a long time ago because I learned when I was a student. I learned Agrada Basic and also the Professor Sakamoto, the mixed problem for the strict hyperbolic equations. So their framework is L2. Because L2, then you have the nice bounded solution. Some of possible inequality, possible equality or something. So you can work in the L2 framework to treat this. But then LP, LP is not L2, Banach space. A long time, there's no nice theory. But then the first year of this century, the Lutz-Weiss proof, the very nice story. So you consider 2 minutes. So in some sense, the solution operator is written in this way. F is equal to, here is some multiplier. Okay, let's say I tau. And the Fourier transform F tau. And the Fourier inverse transform. We say this is multiplier, Fourier multipliers. And the M, now M is not the scalar, it's operators. It's the operator for each tau is the bounded linear operator from some x, f to the Banach space E to F. And then we assume that this is UMD space, but then forget the details. But anyway, this situation, if M is so-called R bounded, is an extension of notion of boundedness, of R boundedness. And then M of tau is R bounded. Then this operator really becomes LP bounded operators. Then if you apply this theory to my representation formula, no, opposite. It's okay. It's okay, yeah. Then you have this kind of nice estimate. So this is the end of my story. So yeah, okay. End of my story is maybe we apply this estimate to our free bounded problem. Then you can show at least the local well-posedness. Meaning is that you can find some short time t, and then you can solve that free bounded problem in this short time t. Uniquely is very important. Thank you very much for attention.
Professor Shibata, thanks a lot for a nice talk. I liked how you started mindly with the definition of the Navier-Stokes, with the derivation of Navier-Stokes equations, and then you showed us this Hill-Yoshida approach for linear case, right? And then the Fujita-Kato approach for nonlinear problems, and then concluding by this, okay, maybe technical, but very, very important case of free boundary problems. So thanks a lot.
Excuse me. One was is now extend to the non-homogeneous boundary condition.
Yes.
It's very different from the Fujita-Kato. Okay.
Excellent. Other questions or comments from the audience? Okay, please. I just give you the microphone.
When you take your surface tension equal to 0, does it make the problem more simple or more difficult actually? Because surface tension can have stabilizing effect, and you can control probably more norms.
Thank you very much. It's a very nice question. And then, yeah, maybe technical answer is, as you said, that the surface tension gives us a regularity of solutions more. Then if you use Lagrangian transformation, of course you can use a Lagrangian transformation, but you lose regulative properties of the solution. If you use the Lagrangian transformation. Therefore, if you consider the surface tension problem, then you have to consider the problems more. You take a local coordinate, and then okay, the surface tension problem case is maybe omega, starting omega is ball or close to ball, and then you have the flow here, and then you describe this surface by using that polar coordinate or something like that. It is one of the way to describe the omega t. This way, maybe you can describe not only u but also the surface function h, and then you have a third order equation for the h, and then you get some regularity. It is a good point. Not a good point. Maybe you should do this one. If you if you consider this Lagrangian transformation, then maybe you don't get the h, and then you lose regularity of the surface. So this means that you cannot solve the surface tension problem using this Lagrangian coordinate. Yeah, but on the other hand, if you do not consider the surface tension, I mean just zero, then you really have to use this Lagrangian transformation. Yeah. Because it's not so meaningful to write the equation from this way.
Right, thank you. Any other question or comment? Yes, please, just a second. Just a second, I give you my microphone.
I have a question concerning the type of spaces. It's possible to replace these LP spaces by some greater class
spaces.
I mean, Lorentz spaces. I mean,
Lorentz.
it's not a question that we just extended
Mm.
by some simple argument, by interpolation or something like this. It is reasonable. In particular, this is weak spaces, weak LP spaces.
I think it's reasonable, I guess.
I mean, my question concerns if we really need to have separability of the spaces or not.
Okay, but in my theory, I usually use LQ. It's a UMD, right? And then we apply the Fourier multiplier theory. But anyway, the point is that you solve this resolvent problem in your space, and then I don't know that if you can solve this resolvent problem. I solved this resolvent problem in the LQ basically, but then the different spaces if you solve, and then you can use the similar argument. It's okay. Pietro, don't sleep. It's okay. Okay, thank you.
Okay, thank you. Anyone else? Any question or comment? I'm happy that we have a number of people watching us online, so perhaps people that are now connected through the Zoom and have a question. So if you have, please speak up. Doesn't seem to me that that's the case. All right. So
hello.
yes, please.
Yes. So I have a question regarding. So thanks
Excuse me.
for the.
Excuse
Hello.
me. Can you introduce yourself?
Hello.
Yeah.
Yes. Am I audible?
Thank you.
Hello.
Hello.
Yeah.
Yes. Am I audible?
Yes, please go ahead.
Yes. So my question is that so there are like when I have studied these things, so there is three ways to study this problem. One is like a sum of two closed operators. One is by the Fourier multiplier. Another is by the using just a variation of parameter formula. So what is the advantage the study of problem by the Fourier multiplier, or what is the advantage to study in the sum of two operators and like that? So what is the what is the advantage to study such a setup by Fourier multiplier?
I don't.
Okay, we report difficulties to understand you because the quality is not so good. But the question was about the Lagrange or Fourier multipliers.
Yeah, this I catch, but then you
Okay,
want
so,
to change the Fourier multiplier theory to some other things, or your question?
yes, like we can study this problem by also like a sum of two closed operator, right? By this way, one can also study the maximal LP regularity.
Mhm.
Yes. So, and also like what you have presented there, like a Fourier multiplier theory. So, what is the advantage to study in terms of Fourier multiplier, and what is the advantage to study the sum of two operators and like the sum of two closed operators? Like, is there any advantage of?
Okay.
It's a very difficult question to answer. I see, understood. Thank you. Yeah, but maybe, yeah, because from my proof, I mean, it's almost bounded is enough. But if we want to use Professor Roots-Wise theory, then always you have to show R boundedness. But what I mean is that to prove the R boundedness, but it is almost the same line as to prove that boundedness. Therefore, you can you can show that our PDE case is a boundedness also automatically implied R boundedness. I hope it's answer to you.
Okay, thank you.
Okay, all right, good.
All right, thank you. Do we have any other questions from the remote people? We don't hear any other questions. So in the audience, everyone is happy. Okay. So Professor Shibata, thank you again for your nice lecture.
Okay. Thank you very much. Thank you. Thank you very much. I'm sorry.